Okay, let's continue with the waves. This is the second slide. I've changed the naming convention, so maybe it'll get arranged properly. And I hope the sound is doing very well. If not, send me an email again, right? So this is a revision of some of the very basics you probably learned in high school physics or maybe college physics, and probably even did some simple physics lab experiments to see the waves and so on, right? So what are the types of waves? We have in the ocean and atmosphere system, we said it's a very special case because you have very heavy water density of 1000 kilogram per meter cube, and air you have 1.25 kilogram per meter cube. So the interface has waves, and the ocean is stratified, as we said, has a pycnocline and then isopycnals within it, and that produces internal waves between the higher density water below and the lower density water above. Very good. So the internal waves, the most interesting thing there is actually hard to explain without all the physics, but the bottom of the ocean, we said, moves very slowly, right? In the other chapter, which means the pressure gradients are also very small. So if you have to maintain the pressure gradients at the bottom to be very small, below, let's say below the pycnocline, then when you move the density surface up, the surface sea level has to change by a small proportion. For example, in the East Pacific, we said the thermocline is shallower because there is upwelling, and sea level is lower and there is high pressure, right? We also said it as colder water having smaller density, occupying smaller space, whereas in the Western Pacific of New Guinea, we had warm waters, deeper thermocline, higher sea level, right? So now we are talking how that sea level is related to the density structure below, or the density structure change. As the internal waves move, they can move by tens of meters but produce just a few centimeters of sea level change. Nonetheless, that adjustment does happen, and what this is showing is a surface image captured, let's say, by a satellite, associate so sea level change, the ripples in the sea level caused by the large tens of meters of movement of density surfaces. So just try to remember it. If you do an advanced course, you'll probably learn why large heaving of the isopycnals can produce small changes in sea level. Okay, there is an adjustment that happens between the isopycnal and the deeper ocean that kind of oppose each other to keep the pressure gradient small, and hence the sea level also small. Okay, so they can be larger than surface waves. We will see that the height of the surface waves tends to be just a few meters at most, except in rogue waves, which it can reach tens of meters. And the internal waves are typically caused by tides sloshing back and forth, a turbidity in the currents, by a ship that's passing by, and also by winds, of course. Okay, these can be possible hazards for submarines. We'll see later that the surface wave perturbations go down to a certain depth, and the heaving of the surface waves can be avoided by the submarine by going below a certain depth beyond which the waves don't reach. But these other processes can cause internal waves which can still affect the submarines. In fact, if the wave fronts are very strong, they can actually chop off the periscope and so on. So the submarines have to be careful about it. What is happening with the wave energy from the winds into the ocean? As we said, waves themselves transmit energy all the time, so they are gaining the energy from the perturbation force, which in most cases is winds, but this chart shows the level of energy and the wave period. Okay, so if you imagine that you're sitting somewhere in near a harbor and you are watching waves go by, and you can watch the crests or the troughs and the time period between them, right? That's kind of the wave period, and 1 hour period gives you a frequency of a number of waves that pass through, let's say 1 minute or so. Okay, wave period is easier to measure because you can see how much time is passing between one crest and the next crest, or one trough and the next trough. So here, very short period waves, 0.1 second to 1 second and so on, up to 5 minutes, are caused by winds. So wind is the perturbation force. The restoring force depends on the period. We will see that a little bit later on. And these are obviously called wind-generated waves. Beyond that, from 5 minutes to almost an hour or up to half a day or so, are caused by earthquakes, volcanoes, landslides, and storms. Storms which can stir up the ocean with much more energy than regular winds, can produce very long period waves. We'll see that there is a relation between wave heights and energy and so on, and wave height is related to how long the wind is forcing the ocean, how strong it is, and what the fetch of the forcing is, and so on and so on. Everybody knows tides, and they are waves as well, and they are mostly forced by moon's gravitational pull. Even though sun is much more massive than the moon, the distance to the sun is much greater, so it turns out that on Earth tidal forcing is much stronger by the moon, and we know that tides occur in diurnal time scale, semi-diurnal time scale, and mixed time scales, and so on. So the period of the tides forced by the moon and the sun go from 12 hours to 24 hours. So you can see the amount of energy that goes in. Winds can put in much more energy in certain places, like the Southern Ocean, where the ocean is a channel, so the winds can keep stirring it. This is very basic. There are progressive waves of the type of longitudinal, where if I tap the table here, you can feel the vibration at the other end of the table, because the vibrations are being passed along the table by molecules just knocking each other in a longitudinal direction. The table doesn't necessarily move up or down, right? When things move up or down, or longitudinally or up and down, they are transverse waves. So imagine you have tied a rope at one end and you are moving the rope up and down at the other end. You can also imagine here that the rope itself is not moving. It's just the wave form that's moving, and that's what is transmitting the energy, right? So it's technically it's not wave speed in that sense, that the molecules are not moving. It's called wave celerity, as we will see later on. So ocean takes the transverse and longitudinal waves and produces orbital waves, and we will go into details. That means basically the molecules of water are making a circle as the waveform passes. In a very idealized situation, it's a circle, but in the real world things are not ideal, so obviously they will have other shapes, as we will see. As I said, this is very basic, and I'm quite sure you've seen it somewhere, but it's good to reaffirm our concepts if in case we have forgotten. So this is almost getting to 10 minutes, but very basic stuff, so make sure you understand all these basic concepts. Okay?